Good morning. Good morning and welcome to General Atomics. My name is Rick Lee and Dr. Boom is here with me, and today we're going to talk to you about states of matter. Now, in the fusion group here, we do nuclear fusion research for the Department of Energy. We do fantastic things using high magnetic field things, and we enjoy what we do with plasma and states of matter. Today we're going to talk about states of matter. And wait, I see Dr. Boom. What are you doing over there, Dr. Boom?
Well, guess what? We have to start out with vacuum. Vacuum is the first thing that we have to put in our vessel or take all the air out in order to make plasma. Now, this plasma goes to 150 million degrees centigrade, and it cannot have any impurities in it. And so air would be an impurity. But I have a vacuum system here, and I have a vacuum cannon. And what this does is I evacuate all the air out of the cannon down there at the lower end, and I have a ping pong ball sitting at the end. Now I have a membrane here. This is a space blanket membrane, and a space blanket membrane down at the other end, and we pump all the air out of this. And when we do that and puncture the other end, the ping pong ball experiences the inrush of air at 15 pounds per square inch, and it comes slamming through this here piece of plastic here, and then it goes shooting out to the other side over here, to the outside. So we want to show you this because it's pretty cool. So I'm going to start up the vacuum pump. This is going to suck all the air out, and we'll watch the gauge come down. And so, okay, now it's running, and you can see the gauge down here. We have a problem here, Houston. Hold on. We have a problem. We have a hole in the membrane.
So, Dr. Boom, this is pretty awesome. You want me to do that while you're fixing that up?
Well,
nope, you got it? Okay.
Just...
So you're evacuating that.
Yep.
Okay, and then you said that ping pong ball is going to go. How does a ping pong ball fly out?
Well, the ping pong ball flies out by the inrush of air through this side over here. And so when I break the membrane with my pen, and so the ping pong ball is sitting right down here, and you can see the gauge coming down. As the gauge comes down, it's less and less air in here. And so we have to get down to about minus about 27 inches or so. And so we have to ask our gentleman over there, okay, he's cleared the area. And so we're going to see what happens here.
Can you give us a countdown?
Well, let's see. We're ready to do it. So you want to put your camera out there, and you won't see the ball going out, except that you might see it going down range. Ready? 3, 2, 1.
Ha ha! It went way over there by those tall towers. I saw it go over there, the orange bouncing one. Wow. And that went fast.
Now that was quite loud. Now it turns out it's so loud because it's a sonic boom essentially with the speed of the air going out through the other end. And so that's our vacuum cannon. Now there's a lot of force with this. This leaves the barrel here, the pipe, at about 600 miles per hour. And so that's quite fast. That's as fast as a jetliner. Now what I'm going to do is set it up for a force demo. I'm going to put 3 soda cans on here, and at the end of our little demo, we'll come back to this and we'll see what happens.
That's very cool, Dr. Boom.
So
if
Rick,
we could get the, we're in a converted woodshed out here, and it's pretty cool, but we're going to have to bring the rolling door down so that we can show you some interesting thing on plasma. We're going to turn the lights off, bring the rolling door down the best we can. And so come on over here, and let's talk about what plasma is. Plasma, if we have a molecule or an atom of gas, it has electrons that go around it. And if we can remove just one or more of those electrons, well, we can have a plasma. We have ionized gas. And so I have a small handheld Tesla coil here that puts out a high electric field that can easily strip away electrons. So I can have this glass tube actually have ionized gas or plasma in it. This particular one is neon, We often hear of neon signs and neon lights. You can see the characteristic orange color that your eyes pick up, but in fact there's a green color hidden down inside of this. Very interesting. So our folks here use spectroscopy to take these different colors and look at them in a very fine detail to understand what's happening in our big plasma. Not so much in one of these smaller ones. Let's see if we have a couple others here and see what colors these are. Okay, a blue one there is argon, and we have a couple more neon ones here. Again, plasma is ionized gas. We've stripped an electron away, and nature has given us two very good handles that we can use to control those ionized species. One is electric fields and one is magnetic fields. So let's take a look at this little longer air plasma we have over here. This is an air plasma right here. This is a long plexiglass tube with a power supply down below. And inside of here is ionized gas. It's air. And if I take a magnet, here's a strong magnet, kind of a yellow magnet, and bring it up to the sides here, it's a little bit subtle, but you can see possibly that the, and let's see, let's get a second one here. You can see that the magnetic field has an effect on how that plasma works, how it moves around in there, the trajectory. Now, changing the trajectory of plasma using permanent magnets isn't very efficient because you'd have to move the magnet back and forth in space. So what we use on our big tokamak are electromagnets. And then that way we can control the amount of magnetic field by controlling the amount of current that's in the electromagnets. Pretty cool, eh, Doctor?
It's very cool. So it'd be really convenient if we had superconducting magnets, wouldn't it?
It would be very nice if we had superconducting magnets. And superconducting magnets, can you remind me what superconducting magnets are?
Well, superconducting magnets use a conductor that does not use up energy as it conducts the electricity. So it doesn't have any resistance. And so the current can continue to flow through the magnet continuously without powering it.
I see. Interesting. Interesting. Yes, that would be cool. Right now, we use standard copper magnets on ours, but we use a lot of electrical current. So the engineers here have to know a lot about electricity and magnetism, and the scientists that work on this have to know about plasma characteristics. It's like having our own little star that we can sit here and look at with 100 different diagnostics.
So how do we power up this here plasma is being powered up by a power supply, right?
Yes, there's a power supply down below here in a manner similar with this, with the this little handheld Tesla coil. This little handheld Tesla coil can show us how we can get electrical energy into another little volume.
Wow, so this one has a green color. And this tube over here has like a pink and an orangish color. Why the difference? What's going on here?
The colors that are given off by these excited or ionized atoms and molecules are characteristic of what the elements are.
Oh.
So, for instance, in the long tube here with the red and the kind of blue, that's air. That's mostly nitrogen and oxygen.
Oh.
With a little bit of argon.
Very cool. So this is like the aurora borealis in a tube or something.
It is like an aurora borealis in a tube.
So
yes.
These are the same colors you see in the aurora. We see like the blues and the pinks and the reds. And
yes, that's right. And that's a very good point. There's a lot of things that we see around here. Everything is naturally occurring, of course, and we can take this on a small scale like this in our little wood shop, or a grander scale like on the whole Earth.
So we use spectroscopy to understand what the particles are inside of the plasma. So it's the same way if we look at stars and use spectroscopy to understand what the elements are on a star.
That's true. And not only can we tell what the elements are, we can tell certain characteristics of the elements, such as how fast they're moving relative to the detector that we're using. We can see if they're going from left to right or going away from us. Wow. There's a lot of things one can do with spectroscopy in a fusion reaction or in a fusion plant or in the stars.
So how fast do our particles travel around our fusion reactor?
Well, they move pretty darn fast, faster than I can go.
They're really honking.
How about you? Yeah, they are.
I think they're running about 400 kilometers per second. That's the estimate I've got. And that's like 1,000,000 miles per hour. It's the same as the solar wind, essentially, the speed of the solar wind.
Okay. So that is pretty fast. It's a little faster than I can certainly run in any time of the day. That's
It's faster
for sure.
than a ping pong ball coming out of the vacuum cannon.
Yes, it is. It is. All right. So let's continue on here with a little bit more of these smaller plasma displays. We have a plasma ball here that is very ubiquitous. A lot of students have plasma balls. And check this out. Check this out, Dr. Boom. I can use the electric field of this to actually excite the neon in this tube.
Wow. Well, if that's red, that's the color of neon being ionized. What about these red spokes here in the plasma ball? Is there neon in that also?
Well, there certainly may be neon in there, but that has more to do with the energy of that last little few millimeters out there.
Oh, look what you did. Look what you did. Take that away for a second. Let me see what you did. Look, you put the fluorescent tube up there, and this fluorescent tube is dead.
That one's not working. How about this one? Try this one.
Let's see. Okay, it's coming on, and look at that. I can pull the plasma right up out of the plasma ball and then put it back in the plasma ball. Oh, I could actually show my friends that. Look at that. Zoom, it's almost like magic, but it's only your hand holding the tube, and that's where the plasma ends. It's the conduction of your hand, so the conductivity of the hand has the governing force there. That's pretty cool.
Right, for that, for the excited gas in there. Not
Now it could
necessarily
become like a
plasma.
lighthouse, right?
Yeah, it looks like a lighthouse. Awesome. Now we've heard of neon tubes and the like, and here's a little neon tube that actually has a green phosphor inside. It has a green phosphor, and this might have been, oh, I don't know, it might have been a bird or something on some sign. But people have been using the concept of plasma and excited gas and fluorescence for a very long time.
So that's not a green plasma.
That's not a green plasma in here.
Well, you had green plasma in your other light bulb there.
I did have green plasma in here, and that's likely due to, I don't know, what, xenon or something like that?
I think it's krypton.
Krypton?
Yeah.
Yes, okay. So we have
There's krypton in that
we
one.
have green in here, krypton.
And there's argon. Well, actually, there's nitrogen and krypton. The nitrogen is from the pink spokes of the plasma, and the green is of krypton. So they put krypton in the bulbs because they last longer. They typically just put nitrogen in these bulbs because they'll last 2,000 hours. But these go into high places, and then you can pay extra money for them, so it'll maybe last 4,000 hours. And so that's a pretty good deal.
So I think what you're telling the students out there with all of these different names like nitrogen and oxygen and krypton, that they need to understand that this universe is made up of these many different elements. And those elements can all be written down basically on one sheet of paper called the table of the elements. It's pretty amazing that everything is made up of those atoms that can make up molecules, and those atoms, of course, are made of protons and electrons and smaller things. So all of that, though, is cool because we have those things right here on Earth.
So there's only so many toys in the toy box, and that's all we get to play with, right?
Yes, but nature has somehow been able to make lots of combinations, millions of combinations, not all combinations, but many, many combinations in the rocks and in the air and the water that we work with here.
Well, in our fusion reactor, we don't put air into it. We take all the air out. What gases do we use for fusion?
So for fusion, we use a fuel called deuterium, which is an isotope of hydrogen. Hydrogen is at H in H2O. It's the simplest element, has one proton and one electron. And we use an isotope called deuterium, which has one proton and one neutron in it. And when we bring two deuterium ions together under the right conditions meaning very, very high temperature, for them to overcome their Coulomb repulsion, or that positive repulsive force, we can get them to fuse and ultimately become helium.
Oh,
So our primary fuel here is deuterium.
so we're in the helium production business.
Huh.
That's a good business. Helium is expensive right now.
It is, and any helium that we would ever produce would be very, very expensive. We would not be able to produce enough helium to sell it on a given good market there. But we do use the deuterium. Now the sun and stars use a fusion process, but they don't use deuterium as their fuel.
No,
they
what
have
do they use?
They have a different recipe. They use hydrogen.
Oh.
Simply hydrogen.
Why can't we use hydrogen? There's a lot of hydrogen in it.
Right. Well, the cross section for a reaction to occur using only hydrogen is relatively low, and we would not get enough fusion energy out to make it worthwhile.
What's a cross section?
So the cross section is overall, it has to do with the reaction rate. It has to do with the actual size of the collision. It has to do with the number of particles. It has to do with the time that they're in there. All kinds of different things. So reaction rates are known in chemistry. They're known in physics. They're known in, even when you're cooking. When you're cooking, there's reaction rates going on with cooking, and you know that it takes, say, 20 minutes to cook some dish. So reaction rates are a time measurement of things happening.
Okay, well that's a good idea. So now, where does this deuterium come from? Where does it occur on the Earth?
The deuterium is awesome. Deuterium is, as I said, an isotope of hydrogen. And while the hydrogen is the most abundant element in the entire universe.
Right, there should be plenty of deuterium on the Earth, right?
Deuterium itself is actually relatively plentiful as well.
Oh.
One out of every about 5,600 atoms of what would be hydrogen are actually deuterium.
Oh.
Many of these are left over from the original Big Bang.
So how do we get the deuterium? It's in water. So if it's in water, then how do we get the deuterated water? We call it deuterated water. How do we get it out of the regular water?
The scientists and engineers over the last many, many years have come up with lots of processes to separate atoms and elements and molecules in a mix of other atoms, elements, and molecules. And so we don't do that here. We leave that up to scientists and engineers at a gas company that would actually be able to do the separation process.
So that's the answer. We get somebody else to do it.
Well, that's part of it. You can't do everything all the time, but they would use techniques that may be based on magnetism or mass separation techniques.
Yeah, well, I would think that they would probably spin it, because the heavy stuff would go to the outside and the lighter stuff would be on the inside.
Well, we'll have to talk to them sometime about how they do that. Right now, I think we ought to take a look at this larger Tesla coil we have here.
Well, we certainly have a big one there.
Yes, so there's a larger Tesla coil here. And let's take a look. So what is a Tesla coil, Dr. Boom?
Well, let's see. Tesla coil puts out a lot of high voltage. And this Tesla coil itself, let me run through the parts of it. In the base of it, there's a transformer, and the transformer takes the wall outlet and converts the electricity, 120 volts alternating current, to 15,000 volts. And the 15,000 volts alternating current then drives a primary that's down, it's a spiral wound coil, the spiral to 15,000 volts. And then that couples into this 1,000 turn secondary, and that boosts the voltage up. That's our paging system here.
So you're saying that we have a power supply.
Yep.
It takes the voltage, which is like energy, out of the wall,
120
and then
volts.
increases it to, what'd you say?
It goes up to 15,000 volts.
Okay.
And then this converts it up to 250,000 volts.
250,000
This
volts.
is 250,000 volts. It's
Wow.
a quarter million volts.
So this smaller handheld Tesla coil I had before, which I was using here, I see a little arc that goes out about maybe 2 or 3 centimeters.
Right. And so that's related to the breakdown of air. And so the gap for the breakdown in air is nominally around 30,000 volts per inch.
Wow.
So you saw that one was about 1 inch long.
Okay. So are we ready to fire this thing off and see what happens?
I think so, yeah.
We should probably stand back, I would think.
Yeah, I'll stand back.
Okay. Let me find the switch here in the dark, of course. We're just kidding. We know exactly where things are.
You got to turn that on?
Eventually, but not yet.
You got to find the hole for the plug? Here. Oh, you got it?
Oh, yeah. No problem. Okay, are you ready?
I am ready.
Okay, I'm going to stand back over here, and let's see what the Tesla coil can do. 3, 2, 1. That's pretty good. So those spikes are going out much, much further than that little one.
That's for sure.
Oh, and what have you got in your hand there?
And I have a fluorescent tube that works.
Oh, and so that electric field is actually getting that going. Wow, hey, I know. Let's see if we can put some of these up on top here. These are the little tubes we had that had either neon or argon in them. Let's see what happens with those. Now, Dr. Boom, do we actually use a Tesla coil here at General Atomics for our fusion work?
No, we don't use a Tesla coil for producing fusion. We don't use it in a fusion reactor.
Okay, but the concept here, the things that we're showing are, in this case, high voltage and some of it's current, low current, things that we do use here, electricity, voltage, concept of
we use
plasma.
coils, we use transformers, and we use high voltage. Our high voltage goes up to 100,000 volts that we use, and then we use that to power up our microwave tubes that heat the plasma.
Okay.
And we also use about 80,000 volts for producing the ion beams that produce a neutral beam that heats the plasma. That's very important technology.
Cool. Let's get this going again, and then I want to see what you had promised us over here.
All right, the
Okay.
vacuum cabinet.
Very cool. This is something we've not been able to take to the actual festival at either Balboa Park or at Petco Park, simply because it's
Too high
not
voltage.
safe enough in the little confines that we have. Okay, can we get the lights on over there, please? Okay, that'll work on the to the right of the. There we go.
All right.
Okay, cool.
So now we're gonna fire up our cannon here. Let's open the door here, and just so what we're gonna do here is we're gonna. That's better. We are going to launch that ping pong ball at 600 miles per hour into these cans right here. We have 3 cans, and we'll see how far the ping pong ball gets through the cans. We know it will go through the first can, but we're not sure how far it will go after that. So I have the ping pong ball loaded, and I'm going to plug in my vacuum pump.
You're going to send a ping pong ball through an aluminum can? I don't think so.
Well, the ping pong ball is moving pretty fast, and so we'll pump it down extra low.
I don't.
So we have extra forces. There it goes. It's coming down. We're down to 25 inches of water here. Actually, it's 25 inches of vacuum. And so 25 inches of mercury, sorry. It would be feet of water. All right, we're coming down. It's getting lower and lower. I think we're about ready. You guys ready?
We're ready.
All right, here we go. Countdown. 3, 2, 1. Holy smoly.
Where did everything go?
Well, it went up to this can.
There's one
here.
can there. One can went into the trash can there.
Well, let's see.
And one is underneath down below.
Down below. Trash can.
One went in the trash can.
Well, here's the ping pong ball.
Oh, okay.
And that's what it looks like.
That's funny.
And
That's funny.
I don't see
So, okay,
Oh,
well,
here it
the
is.
can went over there.
There's the can.
You can see the ping pong ball came out with such velocity, and when
There
it
you
hit
go.
the aluminum can,
There you go.
it transferred the. Look at that. It transferred its energy and momentum to this can and actually just kind of ripped it apart. Look
There
at
you go.
that. So it would have gone in this side.
That's the one that
Gone
went
in.
through. And this one was second, and that one's third.
Okay. So it went in this side on the green and then came out on this side. So all we're looking at here is the concept of vacuum and pressure, and also inside of there, there's no resistance due to air inside of there. So
right.
not only is it a differential of only 15 psi or 760 torr, there's actually very little, if any, resistance due to the air stuff in there.
Right.
That is very awesome. That is very awesome. So Dr. Boom, we talked today, let's have a brief recap. We talked today about vacuum. What else did we talk about?
Temperature,
Some
density,
temperature, density,
electrical conduction, high voltage,
high voltage.
pizzazz.
We talked about elements. We talked about fusion. We talked about plasma. We talked about all kinds of things here. So it's been a great little time that we've had. We can't go over everything, but we do appreciate you being here. We enjoy our work.
Oh yeah, absolutely. It's a great career to be into because there's always something new. That's why I got into it, because there's always something new and different every day. And you can Google this stuff online. You can look up fusion energy. General Atomics has a site for fusion energy. Princeton Plasma Physics Lab has a site for fusion energy. And the biggest machine in the world is being built in France. It's called ITER, I-T-E-R. And they have a great site for fusion energy. And what's going on over there? The machine in France is going to break even, and it's actually going to produce a net gain of energy. It's supposed to produce a gain of energy of 10. So they're going to put in 100 kilowatts, 100 megawatts of energy and get back a billion watts of energy. They expect to. Now this will come online in somewhere around 2025, but then it'll actually put in the fuels to make fusion energy productive in about 2033 to 2035. And so pay attention to the fusion world effort, because it's going to happen. And the United States is now building up an effort to hopefully make something happen by the 2035 timeframe. And so it's a very exciting field.
It is a very exciting field, and General Atomics is, of course, working to promote a lot of good stuff in this field. And our background is such science and technology. We hope that you, too, can continue in your science and technology endeavors. Thank you.
Super cool, you guys. Super cool. Thank you.